The Taurus Report is the bull in the china shop of cosmology. Today we're going to break the standard theory of black holes. Before we do that, however, we should discuss what is the standard theory of black holes. I mean, nobody's ever been to one. And so where does it come from? As you might expect, it has something to do with general relativity. The thing that Einstein needed and therefore obviously allowed in general relativity was to be able to either stretch or compress space at will. Now also, because in general relativity, gravity is sort of a one-way street. You know, the more mass you get, the more powerful it gets, and so on and so forth. So eventually, if you get a large enough mass of gravity together, it is so strong that nothing can escape it, and even the atomic repulsive forces, whether you're talking about nuclear forces or you're talking about electromagnetism, all of the things that sort of would fight against gravity, the way that normal objects in our day-to-day experience do, like gravity of the Earth doesn't pull you all the way to the center of the Earth. And why is that? It's because the electromagnetic forces have a repulsive characteristic in the atoms and molecules that make up the matter we see around us. If that was not the case, then of course you would just sink right through the floor all the way to the center of the Earth if there were no repulsive forces at all. Well, because in general relativity, gravity is a one-way street, which I believe is wrong. I think that's a mistake. But because gravity is just a one-way street, always attractive, once you get a mass large enough, it is so strong that even the repulsive forces within the nucleus itself are not strong enough. And so everything compresses into this tiny pinpoint we call a singularity. And so I'm going to kind of draw a little bit what that looks like. The idea for a black hole is that you get so much mass, it all compresses so that it just becomes a pinprick, something the size of a pinhead or less. It's a region of infinite density and no size. Everything collapses because the repulsive forces, electromagnetic and nuclear forces, are not strong enough to resist gravity, so it just compresses to a region that is infinitely dense. And this sort of thing is allowed because once general relativity opened the door for the stretching and deforming of space, you can just take it to any extreme you wish. And so here, space is compressed so tiny that it doesn't even have a dimension. So an infinitely dense region of space called a singularity. Now, standard theorists, for the longest time, they kept saying that, there's this singularity at the center of black holes, and they also kept maintaining that there is a singularity at the beginning of the universe, like at some time the entire universe was compressed to the size of a pinprick or something. Now, the interesting thing to me, well, you know what, I'm going to get to that in a minute because I'm going to switch videos. Let's continue with the structure of the black hole, and I'll come back to that. So anyway, so you got this singularity at the center of a black hole, okay? And then at some distance away from it, I don't know, however many miles or meters or whatever it is, I don't know exactly, you have some region of space that they call the event horizon. And what is that event horizon? Basically, it just means anything that crosses this imaginary line called the event horizon, anything that crosses it cannot escape. There is no way to escape. It is going to go to that center and be crushed in. So, and that includes light. So light cannot escape here. And if you had a ship, no matter how strong your thrust was, it would not matter. No matter how strong your thrust was, there's no way you could escape once you cross this event horizon. And all of this just logically follows from the general relativity view of gravity, where you can have space stretched or compressed, to an infinite degree. Now, to go back to something I mentioned earlier about the singularities, there are several annoying things I've encountered when discussing these kinds of things with standard GR-LCDM astrophysicists. And one thing that really bothers me is since this stuff we've been seeing in the Webb telescope and everything, and recently I've run across a lot of them, they're suddenly saying like, oh, we never said there was a singularity, or not we've never said it. It's like, oh, cosmology has gone past that. Like, no one has been insisting on that anymore. No one's really saying that anymore. And they're like that whenever GR-LCDM, we start discovering things that might start contradicting it. Then whatever we discover, they just kind of jettison that, and they say that the central idea of GR-LCDM never really implied that, okay? As if the singularity thing at the beginning of the universe and at the heart of black holes are not implied by GR, and yes, they are, okay? You guys, you're just lying. It's a logical implication of the theory you subscribe to. And just look at this. If, they say, modern versions of the theory don't really subscribe to that or whatever. So if I go to something like, let's say I go to the MNRAS website, Monthly Notices of the Royal Astronomical Society, so MNRAS, and we go to their website. Like, let's go to their website. Okay, and then let's go to their search, and let's suppose I type in, this is just one of those big astrophysicist websites. Okay, so I type in like singularity. Okay, and I search. Okay, well, immediately you've got like how many results? Okay, 4,800 results, and let's sort by date. Newest first, okay. So what? We've got stuff in 2023. How many? Hundreds of papers from 2023? We haven't been in 2023 that long, or 2022. And so the point I'm trying to make is that when they say these things are not necessarily part of the theory, that's baloney. Okay, and so I just wanted to make that point, and some of them are doing the same thing as regards the Big Bang, where when you say, the Big Bang automatically means that there must be this very hot, dense state that is the source of the microwave cosmic background radiation. And it's a logical consequence of GR. It just is. And so now, sometimes when I'm discussing it, somebody will come at me saying like, well, modern theorists, have varying ideas of the Big Bang, and you're presenting just one, primitive version of it from far back, and you should be more educated, if you want to talk about it in this modern thing, in this modern way. And again, these guys are so dishonest. That is such baloney. Same thing, you could go to the MNRAS website and you put in quotes and type in Big Bang, and, thousands of papers come up on it. Okay, so these things are central to GR-LCDM, or if not central, they're at least a really logical consequence of making these assumptions that Einstein made in developing GR. And so it is very annoying having to wade through this type of dishonesty when you're trying to discuss something. So I am saying that view of black holes, where you've got this singularity at the center and this what is it, the zone of... So I am saying the GR version of black holes, where there's a singularity at the center and an event horizon somewhere, point of no return, that, and the singularity being a point of infinite density. I am saying that version of a black hole is nonsense. Now, I still believe in a different kind of view of what a black hole might be, and that is based upon CGC, Cyclic, Gravity, and Cosmology. And so I'd like to explain to you what a black hole might look like according to CGC. So in CGC, gravity, of course, is, if you graph the strength of gravity by distance, you will see gravity is like a waveform, depending on the local context. And there are regions where gravity is stronger than GR would predict, and there's regions where it's a lot weaker. And there are even regions where it might be repulsive, depending on the context. So to take a look at this again, and then I will get to how that relates to black holes. So to take a look at this again, if you open up a browser window and you type in Torus Report, all is one word, torusreport.com, then that will take you to my website. And notice at the website, you can listen on Spotify. There's a version of my work on Facebook, and you can click any of these links. This YouTube link here, if you click on that, will bring you to the playlist of the Torus Report, where you can see all of the episodes in order, starting from the first one to the present one. Now, going back, also on my website, if you scroll down, you will see a link to my paper, CGC, and if you click on that, and then I like to download it and change the view. So the view I prefer is to fit with. So view, zoom, fit with, and there we go. Now if you scroll down to, let's say at the level of a solar system here, what section is that in? Here we are. So this is in section, it is in section 4. So in section 4 of my paper, there's a graph of, and it's a hypothetical graph. Again, I'm not claiming that this is what gravity looks like in our solar system. What I am saying is that in general, CGC allows gravity to vary like this. And in this solar system, it shows the strength of gravity by distance. And these green dots are the planets. And purple is Newtonian. And so I show how you could have a CGC version that is consistent with observations. This green dot here is a Oumuamua, by the way. This is Mercury, and so forth. But my point in showing this is that under CGC, gravity varies kind of as a wave function, and in certain contexts, gravity might even be negative, which would mean that gravity is repulsive, which would be forcing things apart. And I'm slowly leading up to how this relates to black holes, and I promise we will get there. I'm just moving my way slowly there. So if gravity is repulsive like that, as I discussed in a previous episode, this means that all masses appear in discrete sizes. And if it's outside that size, then it might get to a point where the surface has gravity actually repulsive. And for example, I think the asteroid Bennu is an example where we see that. It was a recently formed asteroid, I'm assuming, of recently conglomerated material, and it hasn't had the billions of years yet to change to one of those discrete sizes I'm talking about. So that's why the surface of Bennu is unstable. Gravity is repulsive right at that surface. And so what this means is that, as I said, all masses in the universe will occur in certain discrete sizes. And this is why I believe that most solar systems, most star systems, when we look out into the universe, are binary. And that just means you have two stars. Most systems have two stars in them. And why is that? And it is because that gravity does, in my opinion, operate according to CGC, which means that there are certain discrete sizes that are stable, and you can go beyond that, and you have this size might be unstable, and you go a bit bigger and it might become stable again. My only point is that there's certain discrete sizes and density combinations that are stable. And if you're outside of one of those discrete size density combinations, if you're outside of that, then it's unstable and the matter gets ejected to form another star. And this is the reason why most star systems are binary. And even if they're not binary, most of them, I'm assuming, will eject some mass to form planets. Jupiter, for instance, I think if it's, I forget, if it's something like 10 times its current size, it would have ignited and become a star. And we would have been in a binary system too. So in any case, under CGC, only certain sizes are stable. And what this means is that this applies also to black holes. And so under CGC, a black hole, once it gets beyond a certain stable size, will get to an unstable size. And so a black hole would eject matter. And so under CGC, no matter how much mass you have, only certain discrete sizes are stable, and so it's not all going to conglomerate. And gravity isn't just simply attractive. It's going to be repulsive at certain sizes. And so you never get this overwhelming gathering of mass where gravity, the more you get, the more powerful gravity becomes, and it gets so powerful that it collapses even nuclei. Under CGC, that simply doesn't happen. Okay, and so then somebody might criticize this view and say then, well, if that's true, we've observed, I think, at least one actual observation of a black hole. So if what you're saying is true, then how could a quote-unquote black hole under CGC trap light? How could it trap light? And I'd like to explain that right now. Section 14 of my paper on CGC explains this. So let's take a look at this. Remember, in a previous episode, I mentioned that one of the properties that neutrinos have is the ability to refract light if you have a density gradient of neutrinos. So this is relevant because one of the reasons why Einstein's general relativity caught on and won a lot of respect was because theorists assumed that gravity would not attract light. Yet, it seemed that gravitational sources bent light. Well, they found that out later. But my point is, under Einstein's theory, he did not say that gravity acts on light directly. What he said was gravity bends space. Okay, so near a large gravitational source, like if this is the sun would warp space around it. So any light beam that came pass near the sun, because space is bent around the sun, the path of the light beam bends around the sun and is refracted. Well, it's called deflection in that case. But thus, Einstein was able to show how a gravity source would bend the path of light even though gravity was not acting on the light directly. Gravity is acting on space, it bends space, light follows the curved path of space. And they did an experiment on this, or I should say made an observation about this in the early 1900s. I forget the exact date. But they observed that this prediction of Einstein's turned out to be true. They saw the deflection of light around the sun. They saw the observational path of some star, I forget which one. But anyways, as we look at the sun, it was like close to the edge of the sun, and the path of the light was bent. And because this was confirmed, Einstein's general relativity won a lot of respect. And it is yet another thing another item where general relativity makes accurate predictions. Now, of course, I'm claiming it made those accurate predictions for another reason, because there's a correspondence. And so let's take a look at this situation in CGC. So according to CGC, neutrinos are attracted to masses, and I'm here talking about cold neutrinos. So cold neutrinos are practically undetectable by us. But anyways, so I assume that there's an increasing neutrino density so that you have a concentration gradient of neutrinos near any mass. Here I'm showing the surface of the sun. And so this red line is the path of light, and it gets refracted by this density gradient. And the refraction here is greatly exaggerated, just to make a point. And so CGC is able to account for this observed phenomenon, but it accounts for it in a way where space is not bent. And what is the relevance? Excuse me. So what is the relevance to what we were saying about black holes? So under CGC, a black hole might indeed be black in the sense that light isn't escaping from it. The light, if the mass is just right and there's the correct neutrino gradient, concentration gradient, then the light would be totally internally refracted. And so observed from the outside, a black hole, according to CGC, would look the same thing as a black hole according to general relativity. So they'd look the same. But what each theory is saying is going on inside is very, very different. Under CGC, a black hole is merely a specific type of neutron star. In other words, under CGC, you do not have any regions of infinite density, and there's no such thing as an event horizon. Whereas under general relativity, a black hole would have a singularity at the heart of it, and there would be an event horizon. And but under both theories, they kind of look the same. You see just a place where no light is coming out of. Now, there is this whole thing about black holes under CGC is relevant for another reason, and it has to do with elemental abundances. And we will talk about that next. What do I mean by elemental abundances? So, because GR-LCDM, they posit that everything started with this Big Bang, and essentially that means that at the beginning of the universe, everything was plasma, just disassociated, not even atoms at the very early stages, but just disassociated particles in this sort of plasma where everything was equal. In other words, Things were not differentiated into elements. Now, if you posit that, then you have to have some sort of mechanism to explain how we get to where we are today with all the different elements, to get, carbon and nitrogen and uranium and whatever. You take a look at the periodic table. If you're going to say we started from a place where none of that existed, it was just all plasma, and then you get to a place where you have all these complicated elements, you have to explain, like, okay, how did you get there? So they have various processes that GR theorists have come up with, nucleosynthesis, and their theory can very well explain, let's say, deuterium abundances. That's an isotope of hydrogen. So GR-LCDM can explain that, okay? But where, in my opinion, the dishonesty comes in is, okay, if you look at lithium, lithium falsifies your theory. You can't explain lithium by your theory. And instead of them saying, well, okay, that doesn't work, it's falsified, they just sort of bracket that, set it aside, and then keep working on other ones. And they've really set a big task for themselves, because if you're going to posit that it all started that way as plasma, you've basically got to come up with solid mechanisms for like every element. And in my opinion, the lithium problem disproves you like right at the start. And before you even go on, you have to come up with some way of explaining lithium abundances. So I mean, how much lithium there is in the universe at large. Now, under CGC, we have a very different thing, and it relates to this stuff we've been talking about with black holes. Because if you say that a black hole can only reach certain discrete sizes, and beyond that it's unstable, and if you say a black hole is simply a neutronium, so it's a neutron star, then this means that under CGC, black holes can and do break apart. So under CGC, excuse me, I have a bit of a cough today, so I'm going to try and soldier through anyways. So under CGC, you have the universe as this endless, perfect, perpetual motion machine where everything gets endlessly recycled. So mass in a galaxy can go into the black hole at the center of the galaxy, then over time it can break apart and be expelled. Galaxies can come and form, get together. You might have a massive black hole at the center, and then that can break apart. And so under CGC, we have this endless recycling. We know that the heavier elements get made through cycles of stars. Like you have a star that doesn't have any heavy elements, like let's say iron, okay? Doesn't have any of that. Well, during the supernova or nova phase, the energies are sufficient to fuse, higher elements like carbon or other elements. And then if you go through a few cycles of this, of nova, supernova, you get the elemental abundances that we see now, because through cycles of nova or supernova, you can have these heavy elements formed. Then they come back to make a star and a solar system, a stellar system with planets and so forth. And so after a few cycles, you end up with these heavy elements. CGC goes a little further than that, in that it posits that eventually all of the elements we see now will eventually, over time, find their way into a neutron star, where those heavy elements lose their differentiation. Okay, iron going into a neutron star is no longer iron, because a neutron star is just one giant nucleus. And so the elements will go back into a neutron star, lose their differentiation. When that neutron star gets a certain size, it breaks apart again, and the whole cycle starts over again. Then you got to build the elements back up from scratch through successive cycles of nova, supernova. And so Again, CGC presents the universe as this endless perpetual motion machine where everything is endlessly recycled. And so under CGC, in a way, we don't need to come up with some explanation for the current abundances of elements, because under CGC, we claim that the elemental abundance we see today is approximately stable forever. In other words, if you look back to the early universe, you're going to see approximately the same elemental abundances. Not exactly the same, because it depends, where a galaxy or a star system is in the cycle. So, as you peer back in time, maybe it won't look like exactly the same, but you will see an approximate stability in elemental abundances. And because of that, CGC doesn't really need to explain it further. I mean, eventually, this evolutionary process and all of the possible points in the cycle you can be at will have to be worked out. So I don't mean to say CGC doesn't have to explain anything about abundances. But, I mean, there's a lot less pressure. Okay, you're just saying that these things are cyclic, and we need to see why, over time, when you have billions and billions of years, why and how this cycle repeats itself. Now, one thing related to black holes that I must still deal with, the last thing I'm going to look at in this episode, is the LIGO apparatus, because the LIGO apparatus is claiming to be observing black hole mergers. And I guess I agree with that. I mean, I believe that they are, in fact, observing what they're claiming to be observing. However, I just define black holes in a different way. And so, to make a long story short, I would just like to look a little more in depth at the LIGO apparatus and its observations next. So if we open up a browser and just look for some explanation of the LIGO apparatus, let's take a look at that. I like Wikipedia for some reason. All right, so anyways, LIGO, Laser Interferometer, Gravitational Wave Observatory. LIGO, what is it? What is the apparatus? So you've got two of them shown here. There's others around the world. One in Washington State, one in Louisiana, I think that is. And what does the apparatus look like? So it's basically two tunnels perpendicular to each other. Oh, maybe it's not a tunnel. It looks like that is like right on the surface, actually. I thought it was a tunnel. Well, anyways, you have two paths perpendicular to each other. Let's see, where is the schematic? There it is. This is the schematic. So here you have a laser source here, right here, and it shoots a laser out, and it comes to this beam splitter. Some of it continues forward, and it travels 4 kilometers. So this path is 4 kilometers. Okay, it hits this test mass, and then I assume it comes back and goes to the detector here. Okay, then this path exactly, and this is important, it's exactly the same length. Same length. Okay, 4 kilometers, hits this test mass, comes back to the detector. Now, if the path is exactly the same, and it is designed to be exactly the same length, if it is exactly the same length, then these two light beams should come back in phase. So if the light beams come back in phase, then there's nothing going on and nothing is detected. If they come back out of phase, it means there has been some sort of vibration. And this is the important part to me, because this is what I'm going to argue with. The people who designed LIGO assumed that if we're detecting a vibration caused by gravitational waves from some distant black hole collision, that there'd be a difference in the length of space in one of the arms. In other words, theoretically these two arms would be vibrating differently. So there would be microscopic differences in the length of each arm because the length of space itself is changing. Okay? And so then when you get some detection of, because the light will arrive at different times, just ever so slightly. I'm talking very slightly different. And this detector can detect those differences. And so what does all this mean? First of all, I want to re-emphasize again. In this case, they showed, two locations. One in Washington and one in Louisiana. And why do they need those two different locations? So here's the idea. The LIGO apparatus is so sensitive to vibrations. Like, you could have a guy walking along the ground a mile away, and it would pick up those vibrations. Okay, it's super, super sensitive. So if it's that sensitive, if it'll pick up, guys walking around, it'll pick up cars, from 100 miles away, it'll pick up all that stuff. If it's so sensitive like that, how can it possibly see some distant signal from, a black hole merger, 100 light years away? Okay, how could it detect that when it's going to be swamped out by all these local vibrations? Well, this is why they had to build them in widely separated places, like the ones we were looking at the map. They're like 2,500 miles apart, and there's others around the world. And they had to do that so that, let's say you have this one over here, it picks up the vibration from some guy walking nearby. Okay, well, if this is Louisiana, the one in Washington's not going to pick up that guy, but it'll pick up, or else the signal from that guy will be so tiny it won't matter, but it'll pick up, some local truck that's driving down a street 30 miles away. Okay? And my point is that each of the places will pick up local vibrations, and they will compare their vibrations with the other station. And anything that is not common to both of them, they delete it. Okay, so I pick up this guy walking. This guy, the other apparatus picks up some local truck. They don't share that in the same way. And so both of them will delete that. And so that's why you need these apparatuses. I don't know if that's the correct plural for apparatus. Is it apparati? I don't know. Anyways, you need several of them around the world so that you can cut out anything local that you're seeing, and they only will count as a valid signal something that they all receive in common and in the same way. That means it's something they're picking up, from way out in outer space. And so that's how they kind of filter out local noise. Now, here is my problem with what they're saying. I say that space does not stretch. So while I agree with them that they're detecting huge gravitational events out in the universe, I would say two neutron stars merging rather than two black holes merging, and they would respond that neutron stars are not dense enough or strong enough to be giving the signal that we're getting, right? A black hole would be basically infinitely more dense than a neutron star, so its collision would be a much different signature. To which I respond that under CGC, gravity can be many, many times greater than what is predicted by general relativity. It can also be many times less. It can be zero. It can be negative. So in a merger between neutron stars, you're going to have all kinds of gigantic effects that are much different than what general relativity would predict. And so it may indeed account for the type of gravitational wave signatures that we're detecting. Now, again, the way the apparatus operates and why it's detecting these things is very different in the two theories. Under general relativity, the LIGO apparatus works because the two arms are going to be, the space will be stretched in each of those perpendicular dimensions in a very different way depending on the direction where the signal is coming from. And so standard theory would explain why the LIGO apparatus works with the stretching of space. I am saying that that is nonsense. Indeed, the LIGO apparatus is detecting these gravitational events like neutron star mergers or even a neutron star breaking apart. But it's just simply a vibration. Okay, the Earth is feeling the effect of that gravity, and the apparatus is feeling the effect of that huge variation in gravity, and it causes a vibration. And the timing of this vibration is an authentic signal that LIGO is authentically detecting, right? But LIGO does not at all prove that black holes are as described in general relativity. So I am claiming that CGC is fully consistent with the results we're seeing from LIGO. So that about does it for today. I want to thank you once again for tuning in to the Taurus Report. And I very much hope that you will check out the video again next week. So goodbye for now.